as I was saying, thank you for the invitation to speak. What I'm going to do with this talk is present a number of methods for handling informative observation, as I say. So it's going to be quite methods heavy, but I'm going to try and introduce everything in a kind of intuitive way, so you can get a good idea of what the method is doing. So just a quick outline for my talk. I'm going to spend a few slides just explaining what I mean when I'm talking about informative observation. And then I'm going to present some methods that have been used to handle, or that have been proposed to handle informative observation in etiological studies. I'm going to say a little bit about how directed acyclic graphs, or DAGs, can help us in this context. And then a few slides just thinking about prediction modeling. And I'll finish with a summary. Okay, so starting with what I mean by informative presence observation, and I should say I'm thinking very much in the context of electronic health records here, or where the data have been derived from some routinely collected source, as opposed to, say, a cohort study where the schedule of data collection is kind of predefined and more regular. So what the essence of this issue is that people who are unhealthier in electronic health records, people who are unhealthier or those who have better healthcare provision, are more likely to access health services and therefore be overrepresented in the data. So, for example, they might have some biomarkers measured more frequently. So they might have their blood pressure measured more frequently. And this is just a little illustration to explain what might be going on. So I have, in the first picture, I have someone who's unwell, or this could be some underlying health condition. And because of this, they go and visit their GP, and then the GP says, oh, while you're here, let's just take your blood pressure. And so this person has some underlying health condition that has meant that the doctor measured their blood pressure, and that the blood pressure measurement was therefore entered into the electronic health record. And so this is kind of shown in this graph here. So first, actually, let me say, I'm distinguishing between the terms informative presence and informative observation. So informative presence meaning that the presence or absence of a data point depends on the underlying thing. It depends on the thing that you're trying to model. So this might be thinking much more in the missing data context. So you might have missing values of sex or ethnicity or something like that in your study. Informative observation is more in the longitudinal context, where you're taking repeated measurements of some biomarker, and the frequency or timing of those observations is informative. And that's illustrated by this graph, which I've taken from a paper by Sisk et al. So these are blood glucose measurements in an intensive care unit, and the two traces are from two different people. And you can see that the red person on the bottom has much lower blood glucose measurements and much more regular, less frequent measurements. And then the person in blue has very high blood glucose initially. And so they have much more frequent measurements taken, presumably because they're trying to monitor that very carefully. And then those kind of gradually reduce. The frequency of those measurements reduces as the blood glucose gets under control. And so this is the essence of what I'm talking about. If you were thinking about your data set, you'd have a lot of rows of data from this blue person and only a few from this red person. So what is the issue with having informative observation in your data? Well, if in an etiological study, or when you're trying to estimate the effects of some variables on your longitudinal process, if you have informative observation, that can bias those effect estimates. Whereas prediction, it's kind of the flip side, because in the prediction context, if you want to predict an outcome, but the timing of those measurements itself may offer extra information about the kind of underlying health of that person, which can improve your predictive accuracy. Okay, so I'm going on to talk about a few methods that have been proposed for handling this. In each case, I'm going to present a kind of intuitive idea of what the method's doing, and then I'm going to show the equations for how that's done in practice. Hopefully, if you're not familiar with the equations, you can still intuitively understand what the method is doing. So I'm going to start by talking about longitudinal analysis more generally, and one of the methods that is very commonly used in longitudinal data analysis is the linear mixed effects model. And that is illustrated here. And so this is a model that's used to model repeated measurements of a biomarker over time. And so what's shown here is the kind of underlying the trajectory of the measurements for two individuals, so the red and the blue individual, and the dots are the measurements that have been taken around, that are measured with some error around those trajectories. And so at age 40, you can see that the blue person and the red person have quite different biomarker measurements. And you can account for this in your analysis by including a different intercept for each person, so a different biomarker value at age 40. But what that does is that introduces a lot of additional parameters into your model. And so the essential idea behind a linear mixed effects model, it's an extension of the linear model for linear regression, and it includes all of these intercepts. So it has an intercept for each person in the model, but there's an assumption made that those intercepts are normally distributed around the population mean. And by doing that, you reduce the number of parameters that you have to estimate for those intercepts just down to the standard deviation of that normal distribution. And you can do the same thing for the time effect, which corresponds to the slope. So it may be, for example, here the red person is declining, their biomarker is declining over time. For the blue person, it's more stable over time. And you can allow there to be different slopes, so different effects of time for each of these individuals, but again with this assumption that those are distributed around a population average. Okay, and so this is that model that's written out in equations. So we have the biomarker here, and here I is denoting the person that the biomarker was measured for, and J denotes the visit or time point at which that measurement was taken. So the first term is the effects of the variables that you would usually have in a linear model. But here we have the random effects. So the random intercept here, as you can see, there's the index I here, which is showing that we have a different random effect for each individual. And also U1I here is the random slope. So we're allowing a different effective time for each individual. But here is that normal assumption that I mentioned, that we assume that U0 and U1 are distributed normally with some variance. And you can also allow for correlation between the random intercept and the random slope. And that would correspond to, for example, it could mean that the higher your biomarker is initially, the more steeply declining the slope. So if I wanted to do a longitudinal analysis like this, but I had an informative observation process going on, what methods can we use to account for that? So I'm going to cover three methods today. And they all have pros and cons, and it's worthwhile saying these are the most commonly methods used, but the methodological development is ongoing. So there are papers coming up all the time with new methods or new varieties of these methods. The first method is very simple, but it's also statistically not robust because it doesn't rely on the kind of underlying statistical model. But this is just say, okay, we're going to adjust for some measure which summarizes that visit process. And that could be the total number of visits, or it could be the number of visits so far for that individual. And so what that does in terms of the equation is the same as it was before, but now we have this extra NI variable. So we're adjusting for the total number of visits for that person. So a more statistically robust method is to use what they call inverse intensity of visit weighting. And this is similar to, if you're familiar with methods that account for selection bias that use some kind of probability weighting. This method is along those lines. And so the essential idea is to, in your model, when you're fitting the model, you weight each biomarker measurement. And so if you have someone who has a lot of visits, and so they've got a lot of measurements or rows in your data set, those are down weighted, and measurements from people with only a few visits are up weighted. And the idea is that you're then balancing out the data that you have from people who have a lot of visits with the people who have few visits, and overall that they contribute the same amount of data to the analysis. So the weights are derived from fitting a model, a statistical model, to the times of the visits. And the weights are kind of, so that gives you a statistical measure of the intensity of the visit process. And we use the inverse of that for the weight. This method is assuming that any variables which are affecting both the biomarker that you're modeling and the visit process are included in that visit intensity model. Okay, so how do we do this practically? Well, if you wanted to use this method, you apply it in 2 steps. So in the first step, you model that observation process, for example, using a recurrent event model. So this is very similar to a survival model, like a Cox proportional hazards model. It just allows for the fact that it's not just one event. So we're not just modeling the first visit, we're also modeling the time to the second visit and the third and the fourth and so on. But typically proportional hazards type models are used where you have some baseline hazard or intensity or risk of that event occurring. And that's multiplied by some dependence on the covariates which are affecting that visit process. And then in the second step of this method, you fit your longitudinal model, but you weight it, and the weight for each observation is given by the inverse of this term in the visit process model. Okay, so the third method that's commonly proposed for dealing with informative observation is what we call joint modeling. And so the idea behind this model is, rather than doing something in 2 stages, that we define a statistical model that models both the longitudinal process and the visit process simultaneously. And so in this model, the longitudinal model is very much as it was before, in that we have a random intercept and we have a random slope. But now the model for the visit, or the timing of the visits, is also allowed to depend on the random intercept and the random slope, and that creates a link or an association between the 2 models. The only The downside of this model is that it's computationally very intensive, so it doesn't scale very well to much larger data sets. This is just showing what that looks like in equations. So the linear mixed effects model is the same as the one we had before. And the visit process model is the same, except that now we allow there to be dependence on those underlying random effects, the U0 and the U1. And again, those random effects are assumed normally distributed. Excuse me. So I'm just going to show some results for some simulated or synthetic data. So the advantage of using synthetic data in this context is that we know what the true result should be because we know the model it's generated from. So this is a simulation study taken from a paper by Gasparini et al. And so what they've done is they've generated data and they've fitted various models to that data to see how they perform. And the models they've fitted are all given different signs on signals, different symbols. That's the word I'm looking for. They're given different symbols in the graph. So these are all the models that I've described so far in the talk. So that the dot is for the joint model. The triangle is for the mixed effects model that adjusts for the total number of visits. The square is the mixed effects model adjusting for the cumulative number of visits. The cross is the mixed effects model with no adjustment at all for informative observation. And the square is the inverse intensity of visit weighted model. I should say there are two sides to this graph. So on the left-hand side is what you get if the observation process is non-informative. So there's no link between the observation process and the visit process. And then all the methods do pretty well. So I'm going to focus on the right-hand side, which is when the data has been generated with an informative observation process. So the various columns specify different data generating processes. So for example, these, the three, the lines from 3 to 5, so the three models here that have been used to generate the data were all generated using a joint model with varying degrees of varying strengths of association between the visit and the longitudinal models. And so what this is showing us here is that you can see the triangles are all pretty way off. So that's the fitted when you fit the model, but you're adjusting for the total number of visits. So there's a substantial amount of bias incurred for those models. There's the joint model on the whole does fairly well. There's a little bit of bias for the mixed effects model with the cumulative or no adjustment of the inverse weighted model. So I guess this is fairly reassuring, but what I would say in terms of the fact that there doesn't seem to be a huge amount of bias from the plain mixed effects model. What I want to say about these simulation results is that so these results are going to depend very much on the underlying model that's used to generate the data, and I don't think this has been explored fully enough yet in the full range of contexts that we see in kind of clinical and medical research. So I think there's a huge amount of work that's still to be done in this area. I'm going to present here, these are some again, it's simulation results from another study by Yu et al, where they use a different method to weight the analysis. So they use what's called covariate balancing weights, and the idea is that if you're trying to kind of compare two groups, you try and choose the weights that most equally balance the covariates between those two groups. And so I realize I haven't put a key here that says what all these bars on the graph are, but the essential idea is that this is, again, is looking at bias in the estimated effect from the longitudinal model. And the brown here is the bias from the plain linear mixed effects model that doesn't account for informative observation. And so in this particular scenario, there's substantially more bias from fitting the linear model. And the other bars here are all various inverse weighted models, with the covariate balancing models being the ones that are showing essentially no bias here. Another paper recently by Du et al. Proposed modeling not just the visits at which a measurement is taken, but any clinical visits that happen in the electronic health record. And so again, this needs exploring more fully. What's the idea? What's the most suitable thing to model in all contexts, whether it's the timings of the particular biomarker you're interested in, the timings at which that was measured, or whether it's all visit occasions that the person has visited the clinic. I'm going to say just a few words about directic acyclic graphs. So this is a way of trying to graphically represent the kind of clinical knowledge in the area about what's going on, about whether there is truly a link between the visit process and the longitudinal and the repeated measurements that are being taken. So this, I've taken an example here from the paper by Farewell et al., where they propose the use of DAGs in this context. So in this outcome, and I should say this is really an illustrative example. It's not meant to be a full representation of what's going on in this clinical context, but just to illustrate the ideas. So the outcome here is the longitudinal measurements of a fetal crown rump length during pregnancy. And in this case, the visits are the ultrasounds that are used to measure that fetal crown rump length. And the ultrasound schedule may depend on the measurement of the crown rump length that was taken at the previous scan, because if there's any concern around that measurement, it may be that you want to kind of scan sooner rather than later. It may also be that the parents are feeling a bit anxious and they request to have a private scan, as well as the ones that they get on the NHS. And so this is a plot. It's a simplified version of the DAG from Farewell et al. And so the idea here is just to show everything that's affecting these processes and understanding the links between them. And so CRL here is representing the crown rump length, and T is the time at which that was measured. And so the crown rump length is being measured on, we've got visit 1 here, we have visit 2 here, we have visit 3 here, and so on. And so that the fetal health is affecting the crown rump length, and the parental anxiety is affecting the timing of the visits, in the scenario, for example, that they request an earlier scan or a private scan. And then the crown rump length from the previous visit is affecting the timing of the next visit. And so in this scenario, because there's no variables that are affecting both the timing of the visits and the outcome that we're interested in, which is the crown rump length, there's no need to account for this informative observation. Essentially, we say the processes are separable statistically. However, if we add an element to the DAG, which is the underlying effect of the mother's health. And if that health potentially affects the fetal health, but also potentially affects the parental anxiety, here you now have a situation where informative observation is going on because there is this factor, maternal health, which is influencing both the timing of the scans and also the measurements that are observed at those scans. Okay, I'm just going to move on to saying just very briefly a few words about prediction studies. As I mentioned, in prediction studies, there's this flip side that the informative observation might actually give you more information about the underlying health of the person, and therefore may improve your prediction. Because I'm focusing very much on the longitudinal context, I'm thinking of the case which I work in quite a lot, which we call dynamic prediction. And this is the case where you want to measure, you want to predict the risk of an event occurring, not just at one time, but also multiple times kind of in the course of that person's life. And that you have some longitudinal biomarkers which help you to do that. And so you have repeated measurements of those biomarkers. And this, just to explain this diagrammatically, so you might have time 0, for example, at which you have one measurement taken, and you want to use that measurement to predict the risk of your event occurring within L years, say, of the prediction time. But as time goes on, you accumulate more measurements for that person, and they haven't had the event yet at this later time point, and so you want to update your risk prediction, making use of all that kind of history of information that you now have about that person. And as time goes on, you may want to predict risk again at a later date. Now you have even more measurements to use, and you update your risk prediction again for that person. And so Rose, Sisk et al. Published a really nice paper which reviewed methods for use of informative observation and informative presence, actually, in prediction modelling. And so the methods they identified that have been used for informative observation are mostly actually quite similar to the methods that I spoke about for the etiological case. So people have used summary measures. So, for example, again, adjusting for the number of visits that the person has had in the past. Similarity measures these are the kind of methods where you try to identify a group of patients who are very similar to the patient that you have, and then you kind of average over their results somehow to predict the outcome for the particular patient you're interested in. And then I'll move on to joint models. So joint models are very similar to the models I was talking about before, where you're sharing random effects between the models, except now you would also include the outcome that you want to predict as another submodel. And then hidden Markov models are quite similar to joint models, actually, except instead of having these underlying random effects, you have an underlying state which you don't observe, but the patient is in some state which is one of a discrete number of states that they could potentially be in. Okay, so that's all the methods I'm presenting today. I'll just summarize first. So before I finish, so as I said, informative observation is characteristic of many longitudinal data sets derived from electronic health records, and is I believe, very context specific to the particular clinical area or scenario that is being modelled, that is being analysed. What has been found is that in longitudinal models, effect sizes may be biased if you have informative observation in your data. but prediction models may benefit from information about the timings of the observations. There are a lot of challenges that are lying ahead. So I've said very little about kind of computationally how you would go about putting some of these methods into practice. What I find is that all of the papers I've mentioned would typically put their code up onto GitHub that they've used in their analyses. I think there's a lack of dedicated software in this space. So there are options, but most of them would involve, so for example, for the inverse weighting, it would involve using a standard software to fit the recurrent event model and then extracting the weights yourself and then fitting the longitudinal model, the weighted one. So you would probably need a statistician or someone who's quite familiar with coding in order to do that. There's also an issue that I mentioned with the scalability of the joint models, that they aren't, that they're computationally too demanding to fit to very large data sets. I think this needs to be explored in a lot more contexts clinically to really understand when informative observation might be a problem and when it might not. And also questions about transportability to other populations and healthcare settings. So for example, I've fitted a prediction model in this particular population in this hospital. Does it transfer to another population in a different hospital? I think there needs to be more work done in that context, especially if you're using information about informative observation, because then it's not just the population needs to be similar, but also the kind of schedule or the how it is decided when to or how often to measure these things would also need to be transportable. So that needs to be explored a lot more as well. So yeah, I say I'm kind of presented some methods today, but I think there's a lot more still to do in this space, and I'd be very interested to hear your thoughts on that. So yeah, thank you for listening.